Okay, and we're back with chapter 14.3. This is P-Dog, and we're going to learn about the ideal gas law. Um, the ideal gas law is different from the combined gas law in that when the combined gas law deals with a set of changing conditions. The ideal gas law deals with status. Okay, this is the status of a gas, what a gas is like right now. What a gas is like in this instant. So, we use the four variables that we've already talked about. We use pressure and volume and temperature and the number of moles. And all four of these are going to be able to describe any particular kind of gas in a very consistent way. Now, what is an ideal gas? An ideal gas is one that is described by the components of the kinetic molecular theory, also known as the KMT. Okay, the kinetic molecular theory that we talked about way back in 13.1. Now, a real gas, however, and all gases are real gases, do not exhibit ideal behavior under all conditions. But the equation, or ideal gas law, is going to predict the behavior of real gases under most of the conditions, where it's pretty close. The equation is PV-NRT. PV equals nRT. We pronounce it PV-NRT, where P is the pressure. Okay, V is the volume. R is, well, we'll get to R in a second. N is the number of moles. And T is the temperature. Okay, R is called the ideal gas constant. Okay, and R is given by this right here, where R equals 0.0821 atmosphere times liters over mole Kelvin. And what this does is when you combine all four of these variables, no matter what kind of gas you have, no matter what the situation, they all, if you assort them by pressure times volume over number of moles and temperature, you will always get this number. This 0.0821 is this ideal gas constant. Now, there are different numbers that we can convert this into based on different kinds of pressures, but this is basically what it boils down to. Now, our predictions, using this equation, we can predict a missing one of the four variables when we know the other three. And that's going to bring us to our next page. Okay, so how do we get this R? Where does this ideal gas constant come from? Well, we know that 1 mole of any gas at STP occupies 22.4 liters. Well, since R equals PV over NT, if you need to see the math, here we go real quick. PV, if we took, hold on a sec here. If we took all of our relationships, and we did this in class, we know that pressure and volume are inversely proportional. And then according to Charles's law, we know that temperature is proportional to the temperature. So the temperature goes up, the volume goes up. We also know that according to Avogadro's law, that our volume is directly proportional to the number of moles. So if we put all of these into one equation, they're going to equal some constant K, which we have turned into and R. Yeah, see like what we did there? Okay. So, because R equals PV over NT, we can plug in the values that we know up here. 1 mole at STP equals 22.4 liters. Okay, standard pressure is 1 atmosphere. The volume is 22.4 liters. The N is 1 mole. And the temperature is at standard temperature, which is 273 Kelvin. And when you do this, the 1 times 22.4 divided by 1 over 273, you get 0.0821 atmospheres times liters over mole Kelvin. So if we change any of our pressure or volume or number of moles or temperature, one or more of the others will also have to change to maintain this constant. Now, our units must be in these to cancel correctly with the units in R. So whatever we're going to have to do, we're going to have to convert our pressure or liters or moles or Kelvin or temperature to these guys so that we can use the 0.0821. So for example, how many moles of a gas at 100 degrees Celsius does it take to fill a 100-liter flask to a pressure of 1,140 millimeters of mercury? Now, we've got some things we've got to change. First of all, we know we need to find how many moles. So that's going to be PV equals nRT. We need to find moles, so we will divide by R and T to get our number of moles. So PV divided by RT is what N equals. Our temperature needs to be converted to Kelvin, and so we're going to add 273 to 100 to get 373. Our volume is 1 liter, no change there, but we do need to change our pressure being 1,140 millimeters of mercury. We're going to need to change that into 1 atmosphere, and so we would divide by 760 because we know that equals 1 atmosphere, and we'll get 1.5 atmospheres. We plug all this stuff in, so we'll draw it over here. Let's move this guy up a bit and shrink him. But we know that PV over RT, so then we'll take our values and we'll plug them in. So we have pressure, which is 1.5 atm, times our volume, which is 1.00 liters, divided by our R, which is 0.0821 liter, atmosphere, mole, Kelvin, and our temperature, which was 373 Kelvin. Now, if you look carefully at the units, you'll see that the atmosphere will cancel with the atmosphere. The liter on top will cancel with the liter on top of the fraction. The Kelvin down with the fraction will cancel with the Kelvin down on the bottom, leaving us with mole on the bottom of a fraction on the bottom of a fraction, which actually makes the mole on top, and it unreciprocates this mole, and we wind up with getting an answer of 0.0494 moles, noticing how all the units cancel. All right, now we can modify the ideal gas law. And since the number of moles, since N equals the number of moles, and moles has to do directly with our molar mass, so our mass divided by our molar mass, or grams divided by grams per mole, then the number of moles actually equals the total mass of the gas divided by the molar weight, or the molecular weight of the gas. So for example, let's say we have, let's do 96 grams of O2. Well, if we have 96 grams of O2, to find out how many moles of that gas there are, we would divide it by what is the molar weight of oxygen. Well, that would be 32 grams per mole, and we would wind up with 3 moles of O2. So we can plug this, however, we can plug that in into our Pivnert. Right there, and we will get, instead of N, we'll get our mass times R times T divided by the molecular weight. So we don't really have to use the number of moles. We can figure out based on the mass and the molecular weight. All right, so to write that in a more clean way, that would be PV equals N RT, but since N equals moles over molar weight, that's going to go in there. So we'll get PV equals mass over molecular weight times RT. And so we can then just extend the fraction bar like that. And that's PV equals MRT over MW. Okay, this variation allows us to calculate the density and the type of gas based on its molecular weight. So the density then is the mass divided by the volume. Or we can take this, move the volume over here to the mass, and manipulate some stuff. Let's make us a little bit more room for this. So if we manipulate this to get mass over volume, we could multiply both sides by molecular weight over RT, and then divide both sides by V, and then we would get pressure times the molecular weight over RT would equal our mass divided by volume, but mass divided by volume is our density, and that can give us the density of our gas. All right, so let's calculate this. Our example is over here. Calculate the density of N2 gas at STP. Let's shrink these guys up a little bit. So if our density equals mass over volume, which then equals our pressure times our molecular weight divided by R and T, then we're going to calculate the density of N2 gas at STP. Well, our pressure, okay, is STP, so that's going to be 1 atmosphere. Our molecular weight is that of N2 gas, which is going to be 2 14s, or 28 grams per mole. Then we will divide that by R, which is 0.0821 liter atmosphere mole Kelvin. And then our temperature would just be standard temperature, which is 273 Kelvin. Well, we plug that into our calculator. Voila, there's our calculator. And we get 1 times 28 divided by 0.0821, and then divided by 273. And voila, that gives us a density of 1.25 grams per liter. And that would be the density of gas at STP. Now, we can also manipulate a different way, where we can actually find the molecular weight of a gas if we know all of the other stuff. If we know that the mass of the gas and R and T and P, we can figure things out that way as well. So, one final thing that I want you to keep in mind about this, about molecular weight versus, ideal gas versus combined gas law, is this. The combined gas law is P1 V1 over T1 equals P2 V2 over T2. This has to deal when it is one gas that changes. Okay, so if it's going from an initial condition to a final condition, if there's something that changes with the gas, we go from a starting position to a final position, we're going to use the combined gas law. If we're just trying to figure out one of the substances, one of the variables of our gas, then we use the ideal gas law. The ideal gas law, Pivnert, has to deal with status, okay, which is a Latin-ish word that is similar to static. And static means unchanging. Okay, or how something is. How something is, not how it is changing. And so what I want you to ask yourself when you do your further homework and you're doing your your assignments, that you have combined gas law. Look for things, because that's the big bugaboo with these, is whether we're going to use a combined gas law or the ideal gas law. And the ideal gas law is when things, you're just talking about how the gas is, that the situation isn't changing. The combined gas law is when you have a gas that is going through a manipulation, that you're changing the pressure, and you want to see what the volume and temperature come out to be, and if you have starting positions and final positions. The other thing to notice is the ideal gas law uses moles. If you are ever asked, if you are ever given or are asked for the amount of a gas in the mass of a gas or the number of moles of a gas or anything like that, if the amount of gas you have, that's talking about moles, and you will be dealing with the ideal gas law in that situation. Okay, have fun on your homework, and this is P-Dog signing out.